All right, we're going to go ahead and discuss problem Sierra 11-33 from page 492 in the book. This is a good example of a transshipment problem and a way that we can set it up and perhaps understand a few things about the way transshipment problems work, especially when they start off as an unbalanced problem. And I'm going to give you a couple of different approaches in terms of how you can solve this problem. So as you see here depicted on the slide, we have a total of 9 nodes. 3 of them are supply nodes, 2 of them are transshipment nodes, and 3 of them are demand nodes. The supply and the demand is both denoted out here in these columns, and you can see the transshipment nodes. We're going to start off indicating that they have no supply or demand, but we're going to play a little trick on the model that allows it to flow through and balance a little later on when we get to Excel. Another depiction of this same transshipment problem is a network representation. So as you can see, we have the 3 supply nodes shown here, we have the 2 transshipment nodes shown here, and we have the 3 demand nodes shown here. And then the number beside each of these nodes corresponds to supply in this case, and then demand in this case here. The costs to ship along the arcs are not shown, just for the sake of clarity. We're going to go ahead and define Xij is the amount of tonnage that's shipped from state I to state J. And as you can see here, the summation of Xij for J equals 1 through M nodes is 260. And then the summation of Xij for I equals 1 through N is 290. We'll talk a little bit about what those what that notation means here on the next slide. So this slide is showing a way that you can illustrate a formulation for a transshipment problem. Again, we have our decision variable declared, or defined I should say, up here, and then we have the 3 elements really of a optimization or linear programming problem: the decision variable, the objective function, and then the constraints. The objective function has a coefficient in front of every single one of the arcs that is feasible. So you can ship from 1 to 4 at a cost of 16 units of capital per tonnage, or per ton I should say, and then you can ship from 1 to 5 and so on and so on. There is such a thing as an arc between 1 and 2 that you could conceptually imagine. It's not shown here because we don't want to ship anything between 1 and 2, so we're not even going to consider it as a decision variable in this model. There's a couple different ways you can handle it. You can just simply ignore it and not list it when such a thing exists. You can put a very large value in front of it, which will drive the objective function away from those types of arcs. Sometimes that's desirable. But in this case, we're just simply not showing the arcs that we do not want to be considered. Each one of these rows then corresponds to a constraint. Here we have a supply constraint for node 1. Here's a supply constraint for node 2 and supply constraint for node 3. Then we have the 3 demand constraints. This is a demand constraint for node 6. Demand constraint for node 7, and demand constraint for node 8. The transshipment nodes are a little bit different. You have to balance transshipment, meaning whatever comes in has to go out. So in this case here, what you're seeing is that for node 4, everything that comes in, depicted over here, has to go out, which is depicted over here. And the same thing applies to node 5, the transshipment node. And then as always with any linear program, you have a non-negativity constraint, and that simply means that all values or all decision values have to be greater than or equal to 0. So an alternative way that you can also show your formulation is with the exact same objective function. However, this time we're going to use some summations to perhaps be a little bit more brief with our notation. And as you can see here, this is the exact same expression as or value that we have on the previous slide. We're just using a summation notation to say that for node 1, j equals 1 through 5, we're going to sum that, and that has to be less than or equal to 72. For our transshipment nodes, again, we have to balance. So anything that goes into node 4 has to come out of node 4. Same thing for node 5. Anything in has to go out. Now, something that we've talked about, but we haven't always introduced, is this concept of a dummy node. And this is an important concept in transportation problems, because what it does is it allows you to turn all of these constraints into equalities, and that has mathematical meaning. And that also has computational meaning. So what ends up happening when you balance is every single one of those constraints can now turn into an equality, and you can solve this problem as a system of linear equations, because that's what those are. Those are all just equations, and they're all linear. And what can be shown, we're not going to go into the detail, but what can be shown is that number one, that reduces the dimensionality and complexity of your linear program when you do that. So that's one of the reasons why it's desirable. And then another interesting aspect is that anytime you have all integers included in both your coefficients as well as your right-hand sides, your decision variables are always going to be integers. That's just a property of balanced transportation problems. Okay, so now what we're going to do is we're going to go to Excel. We're going to talk about this problem in Excel. So I got a little bit of a jump start here just for the sake of time for this video. And you can see that we have our transportation problem laid out a little bit of a different format. And what this is simply showing is this is showing the parameters, the arc costs, which are inside of this box here of shipping from any node to any other node, to include nodes to themselves. This is a very common way that transportation problems are formulated. And then over here you have the supply, and then down here, I should have this typed in, we have demand. So the costs are no different than what was given in the problem. There's just a couple of subtle nuances here. One thing that you'll notice is you should notice right away that there's a zero cost to allow the transshipment nodes, Indiana and Georgia, to ship to themselves. And you'll also notice that the demand and supply for each of those is 290. And the reason why it's 290 is because what we've done here is if you sum up the total demand, or you sum up the total supply, it's 290. So we know that we can't push more than 290 through this network. If we set the transshipment supply and demand to 290, what that does is that allows this solver to push 290 units through either of those transshipment nodes. Now, in the event that 290 units is not efficient for some reason to go through, or maybe a portion is the efficient portion to push through, and the solver will find that for us, then what will happen is the remainder will get just simply shipped to itself. So that transshipment node will ship the remainder to itself, and it'll satisfy that supply and demand constraint. So let's why don't we go ahead and see if we can set this up. So what I'll do is I'm just going to copy this portion here, and I'm going to paste it right below here. All right, and then for any of these cells that have a number in them, I'm going to go ahead and I'm going to color those yellow. That's a color I like to give to my decision variables. I'll do the same here. This is also yellow, and then the same here. Okay, once I've done that and I've identified the cells that are decision variables, I'll just delete because those values don't need to be in there. Those are the costs. And then over here, what I'm going to do is I'm going to establish the left-hand side for each one of the constraints. So in this case, it's the sum of all the decision variables, and that's what this big box, this matrix is representing. It's the decision variable values. It's going to be the sum of the row, so it's everything that's shipped from Ohio. Click down, and I like to color these green. Okay, now we're going to go ahead and sum up everything that gets shipped to Ohio. obviously Ohio is a supply node, so nothing. We're not expecting anything to get shipped, but you can still use this general format. And then what we'll do is we'll tell Excel to only change values that are in these yellow cells, and that simplifies it a little bit for Excel. Now we have to establish our objective function, and that's going to equal the sum product, this matrix here, and this matrix here. Hit enter. This I like to color red. Okay, now we're ready to go ahead and plug our values into Solver. So I'm going to hit Solver. Looks like some of my previous work is left in there for some gremlins. Okay, so Solver, we're going to set the objective to L14. It's going to be a min function, changing the variable cells. So the cells that are going to change are just the ones that are highlighted. So I'm going to go ahead and highlight these, and then I'm going to type a comma, and then this allows Excel to simply accept this as a range that it will consider, and it'll only change the values in those ranges. Okay, again, these are left over from my rehearsal. So the two constraints are going to include a supply constraint and a demand constraint, and we can get away with that. We don't have to worry about the transshipment constraint because we took care of that up here when we established the demand to equal the supply is 290 for our transshipment. So we're going to go ahead and add this vector must be equal to this vector here, and then this vector here must be equal to this vector here. Okay, so now we have our objective function set, minimization, decision variables, two constraints and equality constraints, again because it's a balanced transportation problem. Make sure we're in the non-negative domain. We're going to use simplex LP. We hit solve, and then we get our answer. So one of the additional things you can do if you're interested in exploring sensitivity of your problem is you can click on the sensitivity sheet and hit OK, and Solver is going to go ahead and it's going to spit out a sensitivity report for you. Now what's typically of most interest in your sensitivity report would be the constraint properties. With these constraints, what's being shown here, particularly in this shadow price here, is it's showing you the amount that your objective function would change if you change the value of the right-hand side of your constraint. So basically what it's saying is if I could get additional resources for some reason, okay, if I could get additional, supply, or if I could reduce demand, where would I want to do that? Where would I, that would increase, or I should say decrease in this case, the total amount that it cost me to move this system of goods through the network that's shown. So that's what these coefficients are showing you here. Now, having said that, what I'm going to do is I'm going to cut the video here, and then when we come back, I'll give you an example with the second part of this video. I'll give you an example of how the book solves this particular problem.